All right, so I'm going to be talking about the Lab 4 circuits. So to start, the intro purpose and key concepts. The main purpose is to predict and confirm the currents, resistances, voltages, potential differences, etc. of different types of circuits, mainly in series and in parallel, and look at the behavior of resistors and capacitors in the grand scheme of a circuit. And through this experiment, my experimental findings in the circuit software either matched or very close to the predictions of what my values would be, which you'll see later in the lab. And my key concepts are the node rule, which is the total current flowing out of a node is equal to the sum of currents flowing into a node, and the loop rule, which just says the potential difference of a circuit is going to be zero with a static electric circuit based off of the round-trip theorem. And then Ohm's law just states that voltage is equal to current times resistance, and capacitance, being C in the denominator of this equation, delta V potential difference is going to be equal to the charge divided by capacitance. So for our first circuit, we have a circuit in series with two 1.5 volt batteries, one 47 ohm resistor on top and a 100 ohm resistor on the bottom. And using the loop rule, I predicted the current to be 0.02 amps. And as you can see in the image, this matches what the prediction was. And when you reverse the connections of the ammeter, the result is exactly the same. And not shown in this picture, but when you replace one of the ammeters with a voltmeter, the voltmeter will read 3 volts and the ammeter will read 0 amps because the connection is broken. The voltmeter still reads voltages due to the battery. And using the loop rule and summing all resistance paths, as you can see in this bottom image, for example, A to B, C to D, E to F, and G to H, the total potential difference was 0. And you can examine this in this graph where you start at 0 and end at 0 with your climbing due to the voltage of the battery. And then when you hit the resistors, it falls off rather quickly because the resistance dimming the effect of the current. And further series of circuit observations. So with a closed circuit and the voltmeter added to the system, the reading on the ammeter does not change. That is because in our system and in our simulation with this computer program, there's technically infinite resistance in our voltmeter. And then when measuring the ammeter reading with the voltmeter at the 100 ohm resistor, like done before, the ammeter remains at 0.02 amps. And then finally, if you replace the voltmeter with the ammeter in parallel with the resistor, rather than in series, you'll get a reading of 0.06 amps. So this is just using our experimental values to confirm that we've been running this correctly, using delta V divided by current to find resistance. So your delta V at the point of the 47 ohm resistor is 0.96. And divided by the current, you get 47 ohms, which is correct. The same goes for the 100 ohm resistor. And then for our wire and our ammeter, there is 0 delta V at these locations. And so there is 0 resistance at the location, which again, with our software is going to be correct. So for our second circuit, the RC circuit, we start with a 10 ohm resistance light, a 9 volt battery, and a capacitor. And so when you connect the system initially, your 10 ohm light is going to light up brightly, and then it's slowly going to dim over time. And then if you remove this battery and just use the discharge of the capacitor to charge the light, the same thing happens. And so when measuring this, when like charging up the capacitor and then removing the battery and having the capacitor charge the light, your 10 ohm bulb is going to have a current that decreases over 7.43 seconds. And when you change it to a 20 ohm resistor in the bulb, the time is 13.78 seconds, which hints at a linear distribution. And so our data model, this is for a measuring resistance capacitance and linearizing our data. When you take a 30 ohm resistor, a 9 volt battery, and the same capacitor we've been using, and essentially over time measuring the volts that are present, and again over time, and then with our calculated resistance RC value, which is resistance times capacitance, linearizing our data to determine an experimental RC value. And so essentially what you do is you take, at each particular time, you take the volt and divide it by our resistance capacitance value. And all these values, and this graph here is going to be our time versus our ln v divided by v naught. And in this equation, as for the line of best fit, this y is equal to negative 0.1666x plus essentially 0. You can find your experimental RC value by doing -1 divided by that slope. -1 divided by negative 1.666 is 6.0024, which is very close to our experimental value is then very close to our calculated value, which is very good. It means we did well. And then for our what ifs, if I were doing this lab in real life and I use an actual ammeter instead of an ideal situated ammeter, the current will be lower because the ammeter and wires and essentially everything that in this lab ideally had no resistance would have resistance. Um, and the same thing for the second what if you're doing this lab in real life and used a real battery charged a real capacitor with no resistor in the circuit. The capacitor would charge slower because there is resistance in the wire, ammeter, etc. And finally, possible sources of error would be incorrect time recording. So just not pausing and starting the time exactly in line with the experiment. Time seconds being placed too far apart, which could alter the data of the line. As shown here, our time segments are at least a second and a half apart mostly. So if they were closer together, it would be more accurate data. And then finally, the software did lag at some point, which made sometimes I would press pause and then it would take a second to stop, which meant that some of the time, again, the time data could be off due to something like that. And that's it.